Welcome to Paramount's podcast number 109, and today we're talking about the second half of this podcast series about vertical airfoil end plates on diffusers. So in podcast number 108, we talked about the theory behind these things and why and what diffusers are, how they work, and why vertical airfoil end plates may or may not work. In this second podcast, so 109, we're going to be looking at the CFD setup, so the actual results, and whether these vertical end plates do work or not. So we're going to finish off the second half of this paper called Study of the Effects of Vertical Airfoil End Plates on Diffusers in Vertical Aerodynamics. So again, this is open access, so you can find it in the link in the description. So let's continue where we left off last podcast. In the last podcast, we were just looking at a few different models that they're going to be looking at. First of all, they're going to look at an armored body with no diffuser at the back or backlight. It's just a rectangular prism with a slightly rounded front. Then the second geometry that they're going to look at is the exact same armored body, but now it has a diffuser. So underneath, behind, like towards the back of the vehicle, there's going to be a chamfer of 25 degrees, and that's the diffuser. Then the third configuration is going to be a rear, the same thing. So it's got the armored body with the chamfer, so 25-degree diffuser, but now it has airfoils at the back. And the thinking behind this was that, so the idea of the diffuser is that we want to reduce the flow, the pressure of the flow going underneath the body to generate downforce, but then the diffuser will now make the flow go back to the free stream pressure. The problem with that is that often in the diffuser area, there is some flow separation. And there's also potential for this flow not to get all the way through back to the diffuser. So there's some inefficiency there. So the airfoils at the back, they are situated such that the low pressure regions will be just behind the diffuser section. And so that will then help suck air through the diffuser area and keep it attached. So in this podcast, we're going to look at whether that was successful or not. So it's quite a novel idea to use these geometries, i.e. airfoils, cambered airfoils, to create the low pressure zones to help control the flow staying attached. So let's continue. This is now the CFD setup. So let's talk about the model and the solver that they used. So the simulations were performed with OpenFoam. So OpenFoam is just an open source CFD solver. It's the best. I don't know of any other open source CFD solvers that come even close to OpenFoam in terms of its accuracy and availability, and what it can do a whole bunch of different situations. So that's what they're using here. And they're using RANs, so they're going to use a K Omega SST turbulence model, which is my favorite. So let's talk about the setup. So they say that the transient solver pimple foam was used to principally observe the development of the vortices generated. So pimple foam is the unsteady RANs solver for OpenFoam. This is different to something called simple foam, which is the steady state version. And so pimple foam and simple foam are the two different ones for RANs. They're using the pimple foam here ideally, which means that they're using unsteady. But to initialize the situation, the case, they say first the command potential foam is run in order to initialize the velocity field solving for potential velocity. So this is like one of the most basic setups you can have, so that it's potential flow. It doesn't have viscosity. So this is good from the point of view that it makes the solution converge much quicker. So instead of going from like the initial conditions, you now have a solution that you've run through this potential solver to get a bit of you're a bit further ahead along the convergence path. Then from there, they actually use the simple foam to run it a bit further to get it to a better initialization. And then they finally use pimple foam, so the transient solver. The reason why they do this is, as I mentioned, to speed up the convergence time, but also to make the solution more robust. So if you were to, for complex geometries at least, if you were to start off transient, sometimes the initialization is so poor that the solution will just crash or diverge. So by using these more forgiving, I guess you could say, initialization solvers, you can then get to a converged case much more readily, and it's more robust. So from there, they talk about the domain and the mesh. So the domain is pretty standard. It's just this armored body in a rectangular box. And they have a view of the mesh. So in figure 10, the side view of the mesh is presented. So let's talk about the side mesh here, because you can tell quite a lot from how the mesh looks. So they say, it is clearly seen how refinement regions are created around the surrounding body, concentrating the cells around it. The smaller refinement region, called refinement wake, concentrates the majority of the cells around the geometry, giving special treatment to those zones critical to the body. So what does this all mean? So they have, for those of you who are listening to this, I'll describe it, or you can always just go onto YouTube and see the image yourself, and or our Spotify channel also has the video, or you can download the paper. This is figure 10. So they have the armored body at 0-degree diffuser, so just the rectangular prism effectively, and they have very coarse cells far away from the body. Then as you get closer to the body, you get finer and finer cells. Now, some things to mention are, one, first of all, there's a boundary layer refinement, the boundary layer zones on the ground, which makes sense because that's a boundary layer is forming there. The rest of the walls do not have boundary layer or inflation layers because they're slip conditions, not no slip. So no slip is when you get boundary layer forming. Slip means you don't get any boundary layers forming. So then another thing of importance is that the refinement zones actually are not just in the wake zones, the wake regions, but also upstream a little bit. So why do we put them upstream a little bit? The reason why is because they're not only downstream effects, but upstream effects. So if, let's say, for example, you have an object and the flow separates behind it, that's going to have an upstream effect. So there's going to be information propagating upstream that we want to make sure we capture properly. So by having these refinement zones further ahead upstream, we can help ensure the accuracy of the solution is high still. If we were to keep the refinement zones just in the wake itself, then a lot of that information would be lost and it would actually make the solution less accurate. Another thing to point out is that going between low resolution and high resolution regions, we do have like this boundary layer, I shouldn't say boundary layer because you might get confused with what I mean. It's not a boundary layer, it's like a transitional zone between the coarser mesh and the finer mesh. And this is just to help reduce discontinuities between these two zones, which could then result in divergence in the CFD simulation. So just by having finer cells, like it goes from very coarse to somewhat fine to a little bit finer, and then finally get to the fine zone at this transition point, you can help your CFD simulation converge nicely and not crash. So that's why they're doing that here. Now, in figure 11, they talk about the Y plus value. So the Y plus value is very important, and for not every CFD simulation you need to have a Y plus value of 1 or less, but ideally, if you do get a Y plus value of 1 or less, you really don't have to think about whether your results are good or not, because you know that they will be good. You're using the right equations in the right resolution. If you know what you're doing, you could always use a coarser Y plus, but you do run the risk of potentially getting it wrong. So let's talk about what this Y plus is, what they're doing here. So they say the average value of the dimensionless wall distance Y plus is around 7 for the 3 meshes that they're considering, and the maximum value is 15. So what does this mean? So as I mentioned earlier, you ideally want to get something called a Y mesh of 1, a Y plus value of 1 for your mesh, and this means that you're resolving the boundary layer quite nicely. If you get a Y plus value of 5 or 10, it means that there's information in this boundary layer that you're not really modeling properly. And we'll talk about how to overcome this in a second. But ideally, you want to be able to resolve these little features in the boundary layers accurately. That way you can tell, that way you have an accurate simulation. Here, they don't have a Y plus value of 1 or less. They have on average 7 and ranging up to 15. They say, to get around this, they go into here now. They say, for values of Y pluses greater than 5, the implementation of Wolf functions is helpful for convergence purposes. So what is a Wolf function? A Wolf function is, I'll actually use Paint here, and I've got my tablet. So let's say we have the wall here. So this is the surface. Oops. And then we have the flow going over it. So we have a regular boundary layer forming. So this is the boundary layer gradient. So imagine, just for those of you listening, a typical boundary layer forming. Now, that's the velocity. Near the wall, where it meets the wall, the velocity is increasing quite dramatically. So if we go just a little bit far away from the wall, the velocity increases quite a lot. We go a bit further, increases again a lot, and then it continually goes up like that until we get to the free stream velocity up here. So because there is such a high gradient near the wall, it means that we ideally want to resolve this region, because if the values of the velocity, not to mention other things such as the turbulence and dissipation rates and whatever, they're all changing dramatically, we want to resolve these things so that we can actually understand, we can actually account for them and see how they propagate through the system. If we have a y plus value of 1 or less, that we are doing that. If we have a y plus value greater than 1, then we're not doing that. What's happening very close to the wall, we're kind of ignoring, even though it is very important. We have very high gradients here, which means that the values are changing very rapidly. So we should really want to resolve those regions. This is where Wolf functions come into it. So what we say is, let's say we have, just for argument's sake, we have a really big cell on the wall. So we don't have a very well refined zone. We don't have, like, instead of having many small cells refining this one zone, we just have one big cell, which is effectively what we have when we have a very high y plus value. So what we do is we say, okay, so in this cell, we are now going to say that using data that we have collected over many experiments, so we can understand generally how the flow is going to change through this cell. So we're saying when we're, let's say, very close to the wall, still inside the cell, the values of the velocity and whatever are going to be a certain amount. When we go a little bit higher in the cell, it's going to change by a little bit, and so on and so on. So we're using this empirical data to fill in the gaps that we have from having such a poorly refined boundary layer. So is this an accurate way of doing things? Generally speaking, no, because often Wolf functions are very general, and most flows are not very general. They are very specific. But if you have specific Wolf functions for certain boundary layers, so for example, over a certain airfoil or over an armored body, then you can get very accurate simulation results then. So you just need to have the right Wolf functions. And they go into what Wolf functions they use here. I'm not going to go into that because that is, like, it's just values that you can toggle. So they have, for example, KR Wolf function, Omega Wolf function, which you can just toggle on in OpenFOAM and apply these ones. And these Wolf functions are for different properties. So for example, Omega Wolf function is for the Omega term in the K Omega SST RANS equations. So in figure 11, they show the Y plus values that they have for all of these different armored bodies. And you can see that underneath the bodies, the Y plus values are quite good. They're actually around 1 or less. This is because the flow is so slow. But as you go around the rest of the armored bodies, they are quite high. They mentioned it's about 7 on average. The airfoils are quite low, so that's a good thing because the airfoils are very important, as we'll see later. So in addition to the Y+, they look at the mesh independence. So they say in order to verify the suitability of these meshes, so they have 3 different mesh, they have these armored bodies, but they use 3 different mesh resolutions. They say a convergence study is performed by Richardson extrapolation and calculation of the grid convergence index. The 3 meshes considered for each case with the corresponding parameters are presented in table 2. So let's talk about all these different terms that we just covered. So we talked about the grid convergence index and the Richardson extrapolation to determine whether refining the mesh more is important or not. So what does this all mean? So in CFD, when we want to make sure that our mesh is good, one way that we do that is we make sure that it's fine enough. So as I mentioned with the boundary layer, for example, let's say we want to make sure that we get accurate results. We can use Wolf functions, but we can also make sure that we resolve the boundary layer properly with more cells. How many cells do we need though? So in this particular case, let's say we want to measure the skin friction drag on this boundary layer, on this wall at this particular point. Let's say we then calculate what the skin friction drag is for one case where we have a certain number of cells, let's say one cell. Then we find that the skin friction drag is whatever, let's say 2, I don't know, it could be anything. Then we increase the number of cells to, let's say, 4, and we see that the skin friction drag has increased to 2.1. Then we can increase the number of cells even more, and we see the skin friction drag is now 2.11. So you can see now that the difference between the first mesh that we had and the second mesh was about 5%. But then between the third mesh and the second mesh is now only 0.5%. So that is a convergence going on there. We know that if we then probably increase the number of cells again, we'd probably not get much of a difference. So then the question is, would it be beneficial to have more cells? If we increase the number of cells even dramatically, like if we have to resolve even more, that's a lot more cells that we have to solve for, which is more computational power, more time, more resources, more money. Is that important to do? So that's what we're looking at here, and these different values is what we're looking at. So let's talk about these different values a little bit more. So in this particular case, they're looking at, they have a bunch of different things. For example, E21 or epsilon 21 and epsilon 32 are the relative errors between the medium and fine meshes and the medium, coarse, and medium grids. So in other words, these are just the errors between these different grids, these different meshes. The parameter R is the convergence ratio used to check whether the solutions are in the asymptotic range of convergence. So in other words, as I mentioned earlier, if the values that we're interested in are converging with increasing mesh resolution, or if they have already converged. So the convergence ratio for the case studies here are quite close to 1. They're actually 1.02, 1.017, and 1.03, depending on the geometry. So they're not exactly 1, but they are quite close. So this tells us that if we were to increase the number of cells again, so we were to make it even finer, we would probably not get much of a difference in terms of the end results. In this particular case, they've said this indicates that the grid is sufficiently refined such that it's considered adequate for their purposes. So they're not going to resolve the mesh anymore. So that's fine. They've gone through that and they've justified their reasons. So let's talk about the boundary conditions now. So the inlet velocity is set at 20 meters per second, and they go out of their way to specify why this velocity is okay. They say a velocity of 20 meters per second may seem small for a Formula One car, but as explained before, diffusers are added to create downforce to improve the cornering speed. When cornering, velocities do not reach very high velocities, but small velocities. For this reason, the velocity of 20 meters per second is set at the initial velocity. So in other words, because they're going around corners, they're going quite slow, relatively speaking. So 20 meters per second is okay. So another thing that's interesting is the thermal intensity level. So I've done quite a few podcasts on thermal intensity level and why it's very important. I'm not going to go through the details here, but the thermal intensity here is 1%. So is that good or is that not good? So they say this value of 1% is reasonable, considering that that's what a lot of wind tunnels do give. So let's talk about a bit more this value and how it applies to real life, and in particular racing cars. So if you go into a typical aerodynamic wind tunnel, the thermal intensity will be less than 1% usually. So it would be around between 0.1% and 1%. 0.6, 0.7% is about average. So that's in a wind tunnel. When you go out onto a track, you could get this thermal intensity level, or you could get a much greater thermal intensity level. It really depends on where you are in the track, who's around you, what the environmental conditions are like. So for example, if you are going very slow, you're just driving along very slowly, even in your car today, if you were to drive home, the velocity that the thermal intensity level you'd find just from the atmospheric conditions would be quite high because you're traveling quite slowly, maybe 50 kilometers per hour. So if you get a 5 kilometer per hour gust, that is 10%. So that's very high. However, if you were to drive at 200 kilometers per hour, a 5 kilometer per hour gust is now significantly lower. It's only 2.5% instead of 10%. So it depends on what speed you travel at. Secondly, if you're traveling behind someone in their car, you have the wake from their car breaking down before it hits your car. And that means that you now have a greater thermal intensity level there. So it depends on where you are in your driving phase and what the boundary conditions are, the environmental conditions are, and how fast you're moving. It would depend on the thermal intensity that you need. So 1% is about an average thermal intensity level across your race, I guess you could say. But it could be a lot higher, it could be a lot lower. And how that affects the airfoil performance, we've gone through in other podcasts, and we'll go through actually probably in the next 2 months. We've got some plans going through that. So I won't cover that here, but I'll just briefly mention it does change the Reynolds number, or it doesn't change the Reynolds number, it changes the effect of the flow over the airfoil like as if you were to change the Reynolds number. So they are equivalent terms. So here they're using 1%. So let's talk about the results and discussion. So we look at how the diffuser works and how the airfoils work. So in figure 14, the simulations performed with a ride height of 20 millimeters show the velocity and pressure distributions. The downforce and drag coefficients are presented in table 3, which we'll look at in a second. But let's talk about the velocity distributions of these armored bodies. So for the armored body without any diffuser, there is a massive wake behind. Like it's just a block going through the air, and as you'd expect, there is a big wake. It's very, very bad. As you introduce this 25-degree diffuser, the wake becomes much better. So it seems to be there's only a little bit of a recirculation zone, but there's almost no wake compared to the original armored body. What about when we put the vertical airfoils on this armored body with the 25% diffuser? When we do that, we can see that the wake drops even more, but there are some slight differences in the flow separation. So there's a little bit of flow separation around the start of the diffuser and around the back of the armored body. And then the flow, you can see, is pushing up at a much higher angle. So before we even get into the forces, from this point, we can already see that there's a greater downforce because the flow is moving up at a steeper angle than any of the other bodies. Even for the body of a 25-degree diffuser without end plates, the flow is moving up at a little bit of an angle of attack, but it's not nearly as severe as this vertical airfoil geometry. So the pressure distributions of these different armored bodies, are also interesting. So when we have just a regular armored body with no diffuser, there is this low pressure zone around the entire system, around the entire geometry. When we put the diffuser on, we can now see that there are these two low pressure core zones, and this, as you'd expect, would be because of two vortices that form. From podcast number 108, we talked about how vortices do form underneath the armored body, so this corresponds very nicely, and we'll get into that a bit more later as well in this podcast. In figure C, which corresponds to the 25-degree diffuser with vertical end plates, we not only have these two low pressure cores, which have also grown in size and their pressure is lower, we also have these low pressure zones around the suction sides of the airfoils. So that makes sense. These airfoils are producing low pressures there, which help suck the flow through the diffuser better. And this also exacerbates these vortices. So in table 3, they have the effects of these different flow control devices, so the diffuser and the vertical end plate airfoils, on the lift and drag coefficients. So without any diffuser, the lift coefficient is minus 0.182. So that's actually pretty good. It means that it's still producing a downforce. The drag coefficient is 0.287, which is actually pretty decent considering that the pack is not even designed to be good at drag reduction. As we put the diffuser on, so the 25-degree diffuser, the lift coefficient dramatically drops to 1.4. So it goes from 0.2 about to 1.4. So this is a 700% reduction, or like a negative reduction, a negative increase, I guess you could say, because you want downforce, not lift, which is huge. So it shows that the diffuser is dramatically increasing the downforce and sucking this armored body to the ground. The drag coefficient jumps by about 2. So it goes from 0.28 or 0.29 to 0.56. So the diffuser is doing very nicely in terms of the downforce, but in terms of the drag, is dramatically increasing that. What about when we put the vertical airfoils on there? Well, the downforce increases even more to 2.14, so about a 50% increase. The drag coefficient also about doubles, so it goes from 0.56 to 1.1 about. So again, that's not great, but it depends on what you want. If you want to decelerate very quickly, having a high drag coefficient is quite good. If you want to accelerate, then not so good. Either way, you get a lot of downforce. So figure 16 shows vorticity planes around the armored body without any diffuser or end plates. And we can see clearly two vortices forming, one on each side, as predicted in podcast 108. So let's move on to figure 17, which shows now the same kind of images, but for when we have the diffuser on the armored body. These diffusers significantly increase the impact of these vortices, it seems, so they are more noticeable and they are higher vorticity, so their maximum is 1,000 1 seconds. So this doesn't necessarily mean that the vortices are stronger. It does mean that they are more concentrated. You can say that. Then figure 18 shows the same plane, but for now when we have the diffuser and the vertical airfoils. And again, we have very concentrated vortices here, one on each side of the diffuser, as we expect. So moving on to figure 19, we have the vorticity of the armored bodies for not only when we have the no diffuser, but with the 25-degree diffuser and the 25-degree and airfoils. And we can see that there is a lot more, as I mentioned earlier. The flow for the 25-degree diffuser plus the airfoil, the end plate airfoils, the flow is moving up at a much greater angle of attack behind the armored body compared to any of the other configurations. So we can immediately see that's where this downforce is really coming from. Apart from that, we do get quite a few vortices, major vortices around the lip of the diffuser, so the inlet of the diffuser for these two other configurations, the one with the diffuser and the one with the airfoils. But for the armored body without any diffuser, there's this massive asymmetry. So because it's close to the ground, no real vortex can really roll up close to the ground. It's really squished. But at the top of the armored body, behind, there is this major roll up, which I have seen in actually our CFD simulations. We do quite a few CFD simulations on YouTube with a lot of like dumb, funny things, and we do often find this exact roll up as well. So if you want to check out those, you can see them on our YouTube channel. So moving on to figure 22, this tells us quite a lot. Figure 22, the pressure coefficient distribution shows how the diffuser inlet, at the diffuser inlet, the pressure decays up to a pressure coefficient of minus 1.5. So what this means is when we get to the diffuser inlet, the pressure has dropped so much, it's gone to negative 1.5, the normalized pressure effectively. Then as we go along the diffuser, the pressure recovers, so it goes close to zero, it overshoots a little bit, then it stabilizes at zero. What does this mean? I covered this in the last podcast where this indicates how much the pressure has recovered. A maximum, like the optimal value is when it goes to zero. That means that it's the same pressure as, it has the same pressure coefficient as the free stream velocity. This means that you haven't, you still have some energy in the flow, but you haven't overtaxed it. So you're getting the maximum efficiency from your diffuser. So that's what's happening here. This diffuser is acting quite nicely, actually. It has a very low pressure coefficient to begin with, but as we go through the diffuser, it recuperates this negative pressure and restores it back to free stream velocity so that it can rejoin the rest of the flow without causing too much drag. So they say, in conclusion, the addition of two vertical airfoils at the back of the body signifies an improvement in the generation of downforce. Hence, adding the aerodynamic elements that create a low pressure zone at the back of the car is a good technique in order to increase the downforce. Otherwise, it must be noted that the drag coefficient is quite high, so it should be considered in order to apply this diffuser configuration or to introduce a new device that reduces the drag produced. So this is quite a tricky thing to get our heads around. So like we have these airfoils at the back of the armored body and they produce low pressures, and this is really good in terms of helping the armored body producing a lot of downforce. But at the same time, obviously it would increase the drag because we have a low pressure downstream, a high pressure upstream, that increases the pressure drag of the object, because if you have the force on the back is much lower than the force on the front on surfaces, because you have a low pressure at the back compared to high pressure at the front. So this is obviously going to increase the drag. So is it possible to not do that but still have a higher downforce? If you want to use a low pressure zone to achieve this high downforce, then the answer is no, because you're by default having a low pressure zone at the back means you do have a low pressure zone. And that is bad for drag. That's what produces drag. So you have to come up with a different way. Another way is to turbulate the flow. There are a few different ways, actually, I should say. First of all, with the current diffuser geometries, where you have a very sharp inlet angle, and that edge there is sharp, you can turbulate the flow to help it have enough energy to go around that corner. Another way is to round that corner so that the flow can go around and not separate. That way you can have a more efficient diffuser happening. So in conclusion, let's sum all this up. For the 25-degree diffuser configuration, the downforce increases substantially with respect to the non-diffuser configuration. And the lift coefficient increases to minus 1.48, 8 times more than the 0-degree diffuser configuration. Last but not least, the simulation of the case of the 25-degree diffuser with the addition of 2 rear vertical airfoils is performed to create a suction zone at the back of the armored body. And this is in the hope that this will increase the downforce. Effectively, the downforce obtained from this last case was significantly greater than the second case with just a diffuser of 25 degrees. The resulting lift coefficient was minus 2.14, about 50% more than just without the airfoils. The region of low pressure at the back of the body can be clearly observed, and this resulted in a drag penalty as well. So that's the end of this podcast. Make sure to like, subscribe, and if you want to check out other podcasts, you can find them in the end screen. And if you want to get better at CFD and or theory yourself, so I went through some CFD here and theory, check out our links in the description below. And if you want to make your experiments 2 to 4% more accurate, check out Atmosphere Hawk in the link in the description. And the reason why this makes your experiments better, 2 to 4% more accurate, is because it accurately measures the density of air for you. The density of air changes by about 2 to 4% on a regular day. And this is due to the changes in temperature, barometric pressure, and humidity, which you cannot really control. The temperature may be, but the barometric pressure almost never, unless you have a pressurized wind tunnel, and the humidity almost never as well. So these errors are in your experiments whether you like it or not, and that means that if you use this data to also validate your CFD will also be erroneous without you even knowing it either. So the Atmosphere Hawk gets rid of that error for you, and you find it in the link description. And I'll see you in the next podcast. Peace out, amigos.